overview of the day. Our official program, I mean, here in this room, goes until lunch. Then I've seen in the program that they say we will prepare packed lunch. I really didn't know whether we're supposed to get ourselves packed lunch or there will be lunch. But, like, we will see. There is a big chance that we will have lunch prepared. Okay, that's nice thing. So what we will do afterwards, I mean, we left on a purpose. You might think that we were lazy, but actually we were not. We really wanted to leave enough times for discussion because that was exactly what several people asked. We would like to have time for work and discussion. As a person who was here yesterday, I could also see that many people were up there in the room. So, like it looks that workshop is really doing what it's supposed to be doing. I'm looking now currently at our hike organizer. If Morna will have some other suggestions to what we could do in the afternoon, like as a group. Same place but the picnic. Okay, that's a good idea. So maybe we will go to the same place but with the picnic lunch. So that's one option. The other option is also, could he propose that he could give up there at 2:00 talk about his latest research. So we will have to kind of squeeze somewhere up there. So like we will find something to entertain ourselves, don't worry. But now let's start with our morning program. So I'm happy to introduce my Anca, who just arrived yesterday, and she will talk about the title you see here. Okay, so Anca, please go ahead.
Thank you very much, Rosika. And I'm very happy to be here among you all in presence. So I followed a little bit online, so quality is great, really great, but it's better to be here and to talk with you, to see you when I'm talking. So it's a talk about communicating systems and how to use automata to analyze communication. The motivation is the general one. So as you know, I mean, everybody knows that concurrency is a hard thing to cope with. So it's hard to write concurrent programs because of various reasons that you all know very well. And it's very hard to verify them because it's very costly in general. And if you look at testing has very low coverage and model checking is too expensive. So it's interesting to have some good automata-based techniques to cope with concurrent programs and to be able to analyze them. So in this talk, I will basically show you some small steps towards distributed monitors, more monitors than controllers. So the big goal is to do synthesis, reactive synthesis, of course. But in general, I mean, that's, as we know, even undecidable or very, very expensive. So in this talk, I will just speak about monitors, how to generate distributed monitors a little bit at the end. Okay, so the setting is communication. So the basic setting, but one should notice that when you talk about concurrent programs in different paradigms, you have some synchronization in mind, and this synchronization can be very, very different. So it can be communication, but it can be also logs. We will see Igor talking about logs, shared memory, rendezvous. And in general, communication is considered to be even more difficult than these paradigms because it's infinite state. Yeah, so communicated systems are doing complete, so it's even more complicated than what we have here. Okay, so we will look at communication, so asynchronous processes that communicate over what? Now you have also big choice. You can have peer-to-peer channels, you can have, as you will see, mailboxes, you can have broadcast. So you can have message passing automata, you can have communicating session automata when you analyze session types, you can have multi-threaded programs. In broadcast, you can have broadcast networks, ad hoc networks, so you have all possible choices. And this impacts a lot on the results. So we need to fix something. So here I will focus on peer-to-peer channel communication and mailbox communication. So peer-to-peer channel communication is the ordinary one. So the classical way to look at communication. So it's in a network. And as you will see, there is also mailbox communication, which has some very, very nice features, which makes it more amenable to model checking. Okay, so let me fix a little bit the objects we are manipulating here, just to have a common language. So message passing automata, these are just, I mean, you have a bunch of processes, client server, and then you have states, transitions, and these transitions, they perform some communication actions. send. So for instance, here, client sends to server message 0, client receives from the sender message $, and so on and so forth. Yeah? So finite set processes, if you want, with some communication actions. It's much more convenient to look at communication in a different way. So you will see also in the talk of Elaine a little bit later, message sequence charts. So that's much better than writing traces of systems, because you have asynchronicity, which makes it difficult to describe all possible traces. So here's a message sequence chart that describes exactly what happens, a possible scenario that is generated by this message passing automaton. So you have the processes, time from up to down, and then the messages that are exchanged between these two processes, C and S. So this gives us the mean to reason about these systems with partial order methods, so to use commutation between actions. And what I will focus on is, in the first part of the talk, on, as I told you, some verification methods for mailbox communication. So not for peer-to-peer, but for mailbox communication. And you'll see in a minute why this is really nice and brings really something valuable. And in the second part of the talk, I will briefly talk about synthesis of monitors. Okay. So if you have any questions, please ask. Please interrupt when something is unclear. So what is mailbox communication? So the idea is that in peer-to-peer communication, you have channels between processes. And in mailbox communication, you just have one mailbox per process. So every process has one inbox, if you prefer. That's the only difference, to have one incoming mailbox per process. And this is something that occurs in lots of modern languages like Rust. Rust has also peer-to-peer, has both peer-to-peer and mailbox communication. Erlang has, Go has mailbox communication. So this is something very common. Yeah? And one could say, okay, so what's the particularity of this mailbox communication? So you will see in a moment. It's related, the particularity of mailbox communication, to one more notion that I will describe now in a second. Something that was introduced by Boisjani and colleagues, a notion called synchronizability. So a message passing system is case synchronizable, K is a bound, if every execution can be rescheduled in a sequence of rounds of size K. So this is, I call them SR rounds. What is an SR round? It's just a trace that consists of sends followed by receives. Not alternating, just sends followed by receives, without alternation. But you will see that has something to do also, one could imagine some alternation later. So it's very common in distributed algorithms where you have, for instance, in the herd-of model, if you heard about the herd-of model, you have a phase where all processes send messages, and then another phase where they receive them. Yeah? So that's something quite common. But here, with this particularity that you fix a bound. Okay. Okay, so the notion is actually related to something that was used in previous work, which is called existentially bounded channels for peer-to-peer communication. But okay, that's another story. Okay, what's particular about mailbox communication? So mailbox communication induces a constraint called causal delivery. So I'll show you on a drawing what this means. So here's a trace. So you can imagine that this is a scenario that is possible in peer-to-peer communication. Yeah? In peer-to-peer communication, that's perfectly possible. So this is the trace that corresponds to these three messages: the red message, the blue message, and the black one. But actually, in mailbox communication, this scenario is not possible. So why is this scenario not possible? Because you have, so mailbox says that actually, if you have an order on the receives, then this induces an order on the sends too, because you have only one inbox. So if you have two sends, they will be received in the same order as they entered the mailbox. Yeah? So basically, because of this order between the two receives, you have an order between these two sends. And here you see a cycle. This is the cycle. So you have this mailbox order and the process order, the message order, and again the process order, and you have a cycle here. So this violates what is called causal delivery. And this scenario is not possible in mailbox communication. So you have less possibilities. But the fact that you have less possibilities has a very nice consequence that some problems will become decidable. So now just let me recap what was known after Boisjani introduced this notion of case synchronizability. So they showed that case synchronizability guarantees decidability of the reachability problem, control state reachability, so in p-space. And there were some other papers showing that, correcting actually a bug here, that given a bound k, it's p-space complete to know if a message passing system is case synchronizable, so given the bound. And they even show that it's decidable to know if there is some bound k such that the message passing system is case synchronizable. Okay, but now you can argue, okay, why should we have bounds? So do we really need bounds? Yeah? So a message passing system is called just synchronizable if every trace can be rescheduled in such a way that it corresponds to an SR round, a sequence of SR rounds, sorry, without any size bound on the rounds. That's important. So we want to get rid of this bound and just have a sequence of rounds, and we ask what happens in that case. Okay, so why is it interesting to combine mailbox with these SR rounds? So the magic happens here. You don't need to store messages. So all of a sudden, this Turing capacity of message passing systems goes away. Yeah? So you don't need to store messages because, so just look again to this example. So this is an example that doesn't pose problems with causal delivery. As you can check, there are no cycles. And here, what happens is that I can give you a trace where the order of the sends, so the black one, the red one, the blue one, will be the same as the order of the receives. And since these two orders, so basically with mailboxes and SR rounds, every scenario that is possible under mailbox can be scheduled in such a way that you have the same order on sends as on receives for each round.
What do you mean store messages? The mailbox store messages? No?
Yeah, but you don't need to do verification. So when you verify the system, you don't need to look at configurations where you are looking at the content of the channels. Because that's where the undecidability of message passing systems comes from. Okay, you can store arbitrary. Here also, you don't have any bound on the channel, but as you will see, when you do verification, you don't need to care about the fact that the channels mailboxes are unbounded. That's the only point. And why? You will just guess the middle state of the execution here. And if I have here the state where I start and the middle state, what I will be doing then is to execute the send and immediately the corresponding receive from this middle state. And then I continue here with the red one, and I will execute the corresponding receive here. So I will progress on this part, and in parallel, I progress on this part. And at the end, I check that my middle state was correct. So that's just an automaton that will guess such a nice scheduling of the trace, yeah, without storing messages. You just need finite states for that.
So why isn't it in NP?
Why it's not in NP? Because you have processes. So you have a polynomial number of processes. So you need to, I mean, this middle state is the middle state for each process. So it's p-space for that simple reason, and it's p-space complete. Okay, so this shows that reachability for synchronizable systems is in p-space. What I didn't tell you is that, I mean, we can work on particular schedulings of traces, reschedulings of traces, because for control state reachability, it doesn't matter. So it's just the control state that matters. So that's enough. Okay. So the results that we obtained, so I obtained with my PhD and a colleague in Bordeaux, is that given a synchronizable message passing system under mailbox semantics, it's p-space complete to check global state reachability, so without any bound on the rounds. To model check synchronous traces against regular properties with some small restriction. To check if the peer-to-peer semantics produces more behaviors than the mailbox semantics. Okay, so these are things that come from the reachability problem being p-space in p-space. And then what's also very nice is that you can check if a message passing system is synchronizable in p-space. So it's p-space complete. So the property is decidable. And it's with the same complexity as reachability. Actually, the property is as costly because it reduces finally to reachability. And all the complexity bounds are actually polynomial if the number of processes is fixed. It's only exponential in the number of processes. Okay, just a small remark is that all these problems, synchronizability, reachability for synchronizable systems, are actually undecidable for peer-to-peer communication. So here is
What is peer-to-peer communication?
you have a channel for each pair of processes. If instead of having mailboxes, you have channels, then all these questions are undecidable. So it really matters, yeah? This causal delivery and the fact that you can order the receives as the sends, you can do it only for mailbox. Okay. Yeah, how much time do you give me? 10 minutes? Okay, so I wanted to give you just a flavor how to show that this property of synchronizability is decidable in p-space. So the idea is that we need to decompose executions in what we call atomic pieces. So this is an atomic piece, sorry, and and this is non-atomic. So what does it mean, atomic? It means that I cannot split this piece, so this sequence chart, into two sequence charts without cutting messages, but that one I can split it. Yeah. So this is an important notion. And now what we are looking for is, as you will see, we will look at atomic pieces that are SR rounds. So this is an SR round because you see the sends here, and then I can do the receives afterwards. So I can linearize this message sequence chart in such a way that I have first all sends and then the receives. So this is an atomic SR round. This is not it's atomic, but it's not an SR round because I have here, you see, a send, a receive, a send. Okay, so this is not a good piece for synchronizability. And then what we are doing is that we build an automaton of exponential size in the number of processes for executable atomic SR rounds. We can find such an automaton, first of all, so for these small pieces. And then we are looking for minimal witnesses for non-synchronizability. And we say, okay, such minimal witnesses need to contain some atomic piece that is not an SR round. And here you have an example. So if you omit this receive here, you can check that this execution is synchronizable. Why? Because I can do this send, and then I can do that one, and then I can do this message. So this will be synchronizable. But if I add this one, it won't be synchronizable because all this piece will be atomic, and you have here the problem with the receive and the send. Okay, and that's how we guess minimal witnesses. So you see here, everything goes fine up to here. And then this receive, this red receive comes, and you see that you build a cycle. Okay, so an automaton can guess all this stuff. And what's important is that we use reachability. For guessing all these parts, we use reachability, and we store some additional information in order to be sure that we have here a path, and then that we close the cycle. Okay, so that will be an automaton of exponential size in the number of processes that will detect minimal witnesses for non-synchronizability. And you check the emptiness of this automaton, and then you have your p space, favorite p space. Okay. Now I go over to the second part where, as Muscholl was saying, we need to lower expectations. So I will show you a case study of lowering expectations. So p space, yeah, p space is p space. So we would like to have better complexity, and actually, so I'm interested for a long time now in synthesis of in distributed synthesis. So I want to turn a property into an equivalent message passing automaton. So that looks hard. And okay, so this turning a property into equivalent message passing automaton, so this equivalence will be meant up to extra message content. So in the sense that I describe you some communication, and then I allow my message passing automaton that will realize this property to add some content, because a monitor, that's what a monitor is supposed to do. A monitor should run in parallel with my system. It should be distributed as my system, but it should be allowed to add some information. So we are interested in looking what kind of properties are implementable, and that's a kind of distributed synthesis. Okay, and let me take something very simple. One synchronizability. So what means one synchronizability? So this is a scenario which is not one synchronizable, because you see, I mean, this is atomic again. I cannot split it into messages. This is one synchronizable because I can split it into messages. Yeah? So let us try to have a monitor that detects if an execution is one synchronizable or not. That looks not very hard to do. Yeah, to be honest, I don't know how to do it in general. So we started to look at hierarchical communication. Hierarchical communication means that you have, it's like in languages like Rust, you can spawn threads. And then when you spawn a thread, a child thread, you can create a channel or a mailbox, as you want, to communicate with the thread. So the communication will be only between parent and child. It won't be, yeah, it's just hierarchical communication. And what one can check is that if the communication is hierarchical, in order to be one synchronizable, you need to exclude such patterns. This is not one synchronizable. So here you can have arbitrary many other things, but this cross means that you are not one synchronizable because you cannot separate these two messages. Okay. Here's a way to devise a distributed monitor for this property of one synchronizability. So I just depict you what happens on the side of the server. So the server will send messages to client and will color the messages with two colors alternately. So here's a phase where sender sends to client only red messages. Whenever a message comes from the client, server will change the color and so on and so forth. Yeah. So that you have an alternation. So this is okay for one synchronizability. This is not okay. You have a cross. And actually, client can detect the fact that you have a problem for one synchronizability here, because client will detect that a red message arrives here, but you see that client has sent the message here, and here the color was the same. So with this color trick, client can detect that the cross appeared, and you can do it, of course, symmetric also on the other side. So basically, you just add one bit of information. You have a question? Sorry?
The colors can go unboundedly long.
Yeah, the colors you will alternate unboundedly. Yeah.
And then do you need to differentiate between the red and the blue, or you can just call the okay?
Yeah, I differentiate between red and blue. So whenever client sends back, I change the color.
But then this count can go unbounded.
But the colors are only two. But this change can go unboundedly, and we fix a color to start with. So the initial state will fix that.
So this number of colors is what? Is it the?
There are only two colors.
That's because you're checking one synchronizability.
Yes.
I see.
Yeah, that's because I take one synchronizability. I don't want to talk about case synchronizability. I can't tell you exactly how to do this without deadlocks. That's the problem, actually. So the trick here is that you can do this monitor. It's a monitor. It doesn't deadlock. Okay. Okay, and now for if we want to do one step more, we can try to synthesize monitors for one synchronizable properties. So if I give you a one synchronizable property, so a property about communication, but it has also the feature to be one synchronizable, so it only talks about messages in this way. I will use the distributed monitor that I showed you to guarantee one synchronizability. And now, if I take a property that is regular and commutation closed, so what means commutation closed? So here's again an example. It's one synchronizable, everything is fine. So commutation closed means, like you can imagine these messages correspond to these A's, B's, and D's, and so on. And you see that, for instance, F and D, you can do them in whatever order you like. So you can do, for instance, A, then B, then F, then A, or you can start with A, then F, then B, and so on. So the property should be insensitive to such commutations. Okay, and such properties, we can monitor them. And how will this look like? So you see here, okay, so I'm focusing on this C here, yeah? So I have my property, and in my property, my property is regular, so I have an automaton for this property, yeah? Okay, so you see the states of this automaton here, yeah? So suppose that you have this automaton, and since the property is commutation closed, you will have such diamonds here appearing, because F, A, and D, F and D, and A and D, they can be swapped. Okay, so in my automaton, I will have this situation. Yeah? Okay, so Q1, so I'm focusing on this C, which is the last one, which appears here. And Q1 is the state that I have reached after AB. So maybe I put here just a small up. Okay, I have. So the B part here is the common information of W and of S, of these two processes, yeah? And now, if I'm just before the C, as you see, I mean, what does W see? So W sees all this part without the F. And S sees, what does S see? S sees this part, yeah? So they have different views, these two processes. Okay. And what happens here is that I will have the information of ABFA, what happened in the automaton. So this state Q2, it will be seen by S, and the other one, ABD, will be seen by W. Sorry. So Q2 is seen by S, Q3 is seen by W, and in addition, W will remember also the state Q1. The state Q1, which was the state reached after the common past of these two processes. And from these states Q1, Q2, Q3, actually state Q4 is determined. So there is a property of this automaton that says that if you know Q1, Q2, Q3, and you know also the processes, okay, on which these parts ran, then you can deduce Q4 is determined. We have a table to do it. So if you know Q4, you know also the state after C, you know the state Q. So after this process, you have the state Q. The only point is that in order that both processes know the state Q, actually it's W who needs to guess Q2. So this is not really a monitor. So there's some guessing here. Yeah, so there's some deadlock possible. And the interesting question is how to do this without deadlocks. So what kind of properties would make it possible to run without deadlocks? Okay, so this was just lowering expectations and the first step in this lower expectations. And the question is which kind of properties, which are regular and commutation closed, I could check without deadlocks. Okay, so this brings me to the end of the talk almost. Just put here some information about previous work on synthesis for communication. So we had some work years ago about synthesis from MSC graphs. So we can synthesize communicating automata from high-level MSCs, regular high-level MSCs, but with deadlocks. Then there is another thread of work with synthesis using projections on threads. So this is the simplest idea one can imagine, that you have a description of property, and then you just take for each process the projection of actions on this thread, and you ask yourself, if you put these projections together as a communicating automaton, what do you get? In general, you can get more than the property. Okay, so, and it's undecidable to know whether you get exactly the property. There is another work by, again, by Rajiv with Stavros Tipakis about protocol completion from a set of MSCs, but this is from a finite set of MSCs, where they start with projections and then add transitions. And there is a more recent thread of work, which is, I find very interesting and would like to understand better. It's about multi-session, asynchronous multi-session types. So in asynchronous multi-session types, they also use this one synchronizability, if I'm correct. And the idea is here to have a generalized notion of projection that helps to infer a message passing automaton from a property. And again, with the goal to avoid deadlocks. Okay. So lots of open questions. So I showed you something to monitor one synchronizability. I have no clue how to do it nicely for case synchronizability. It gets much more weird. And then the most important question that rises here is how to synthesize monitors for properties without having deadlocks. Yeah? So deterministic, without deadlocks, which properties can be monitored without, so in this setting. Okay, thank you very much.
Maybe this is a naive question, but I'm missing something about the difference between mailboxes and peer-to-peer.
Yeah.
Isn't a channel a process with a mailbox?
So in peer-to-peer, you have. So if I go back to, let me see.
You see, you have channels, but can't we model a channel as a process with a mailbox?
Of course, I mean, everything that you can do in mailbox, you can do it also in peer-to-peer.
No, I'm asking vice versa.
So vice versa, you cannot do it. And this was exactly my example where I told you that you have this causal delivery. So this is something that you can do in peer-to-peer without any problem. You have a channel from C1 to S, you have a channel from C2 to S, a channel from C2 to C1. Yeah? So this is something that you can do. You see the drawing, you forget about this arrow, you can do it. You cannot do it in mailbox semantic. So with mailboxes. Why? Because S has only one mailbox. So it should receive from C1 before.
No, but what I'm saying is you need to draw a more complicated picture where the channel is also a process. Right now, you're not drawing, the channel are invisible here. Make the channel, model the channel explicitly as a process with a mailbox.
You could do this. You could do this. You could add more processes and make, I mean, yes, that's true. But you see, I mean, in terms of reachability, things will go wrong because if you have this SR rounds for, I mean, you will get special peer-to-peer communication if you do this.
But this suggests that something is wrong with the channel model because at the end of the day, it's a physical thing.
Yeah.
So it's a process. A channel is a process. We are kind of not modeling it, so it disappears.
Yeah.
But physically, it's a process.
Yeah.
And it's a process with a mailbox. So it suggests to me that something is wrong with the channel model. It's unrealistic model.
Which one, the peer-to-peer or the
peer-to-peer?
That's networks. I mean, that's...
A network is a physical thing. There is something physical there.
Yeah.
Now, typically, we abstract it away.
Yeah.
And so it's the ether, okay?
Yeah.
But in reality, it's a cable. It's a process. And unless
but it stores messages. But it stores messages. I mean,
so does a mailbox. So does a mailbox store messages?
Yeah.
So what I'm saying is, explain to me why a channel is not a process with a mailbox. How is it different than a process with a mailbox?
You can view a channel as a process with a mailbox. There's no problem in that. So the question is what you gain.
I think you're getting a more realistic model.
I mean, there's a difference in terms of the semantics, I think. So you cannot simulate, I think, a peer-to-peer, arbitrary peer-to-peer communication with just mailboxes, right? Because I mean, if you add a process per channel with a single mailbox, then you still need to. I mean, all those processes need to somehow communicate to get exactly the same behavior as the peer-to-peer communication.
So I'm wondering whether the peer-to-peer model is too abstract, unrealistic, and maybe less interesting.
I mean, it's, for example, in Go,
dual.
I think you have exactly that model. So you have so when you do a round of communication, you can select over a couple of channels and select from one of them, and then, for example, receive a message. So it is, and then I mean, each of these is sort of FIFO.
But ultimately, it has to be compiled. It has to be compiled to hardware.
But to hardware, I mean, you have the links and you have your messages in transit. I mean, that's the.
I still think that there is a possibility that we abstracted too much. We created an unrealistic model by abstracting away the channel is a process with a mailbox. But let's move on.